Good morning, everyone. This is Adam Groves with PTV Group. Thank you for joining and welcome to our first installment of our PTV Talks series. We're beginning with CoExist, preparing the transition to automated vehicles with PTV Vissim. This will be our first session in a series of regularly scheduled PTV Talks, where we hope to offer informative and educational sessions from PTV staff, from clients, and from industry leaders. As we kick off the series, we'd like to encourage you to offer your feedback on possible topics, the formats, and any additional feedback that you may have that you think will make the sessions more useful. We will be doing a Q&A after today's presentation. You should be able to submit your questions during the presentation by using the questions panel on the GoToMeeting. And now, without further delay, I will turn it over to today's presenter, Alistair Evanson, our Solution Director for PTV Vissim.
Hi everyone, and welcome to today's webinar where I'm going to be talking about CoExist, which is a project that PTV have participated in, looking at the transition for autonomous vehicles and how we can actually simulate those with our product PTV Vissim. Alongside me, I also have Dr. Jochen Lohmiller, who is the manager of our PTV Vissim product management team here in Germany, and he'll be assisting me with answering questions during the webinar and also during the Q&A at the end. Okay, so on to today's webinar. First of all, I'm going to provide a brief introduction to the project, identifying the aims of the project, the partners that were involved, and then move on to some of the details around the study locations and also how we actually undertook the scheme. Then we'll look at some of the core tasks that we undertook, what our actions were, and finally onto the outcomes, how we've actually taken this research project and using autonomous vehicles and built functionality into our software PTV Vissim. Okay, so what is CoExist? Well, the clue really is in the title for CoExist. So it's a project that looks at the coexistence of human-controlled and automated vehicles within our road infrastructure. It's a project that was funded by the European Union as part of their Horizon 2020 initiative. What we look and aim to achieve from the project is that we develop an AV-ready framework which will apply for road authorities to help them understand a little bit more about the transition from human-controlled to automated vehicles. So we were looking at different cities around Europe, different types of traffic compositions, especially in that context of having the coexistence of automated and conventional vehicles. And then really the outcomes from these projects is enabling those road authorities to have a bit more detail when thinking about the impact of increasing numbers of automated vehicles, so that the changes and plans could be made to infrastructure in order to accommodate new technologies and varying degrees of technologies as well. So a little bit more about the mission, and on the right hand side of the slide here you can see the partners that were involved in the project. So we had a number of technological partners, some partners from the automotive and equipment manufacturer part of the world, and also a number of cities and research agencies that are based in Europe as well. And really, the mission was to give road authorities the tools that would allow them to start looking into these challenges that they face in the mid to longer term future about how to integrate autonomous vehicles and connected autonomous vehicles on the road network as well. So when we could simulate those vehicles in different European cities, then we could understand a little bit more and provide those authorities with the types of guidance that they need about how they could actually get AV ready. Now, we looked at achieving this through a mix of both microscopic modeling, where we look at it in a high level of detail at individual vehicles and individual vehicle movements, and we also look at a macroscopic perspective as well, which is where we are starting to look at the impact that those autonomous vehicles could have on general volume to capacity ratios across wider, larger kind of strategic models as well. Okay, So really, this topic is about how we can start to look at different scenarios and how we can start to perhaps bring some level of certainty to something that is really quite uncertain. So at the moment, we don't always have perfect information when we want to tackle this aspect of autonomous vehicles. So it might be that we understand quite a lot about the dynamics of the vehicle, how the vehicle will operate when it's in an autonomous mode, but then on the other side, we don't understand what the human acceptance or the consumer acceptance of that technology might be. So we have information on one side, but not on the other. Vice versa, we could have good information about the penetration rates and the user acceptance of the vehicles, but not really an understanding of how they would interact with other traffic, how they would actually operate when they drive around our roads, when they're on our highways, our interstates, and so on. So really, we look at the type of assessment that's being done can be made on assumptions, and these kind of assumptions can vary quite widely, and that can lead us to doing a lot of different scenarios where we perhaps alter some of those assumptions by a small amount, and every time we alter those assumptions, we'll get a different result. Now, we need models to evaluate those assumptions, and really, as part of this CoExist project, it was identifying how we can take some of those assumptions that we currently have and provide a little bit more certainty about them. So how we can actually understand a little bit more about how those vehicles would drive on the road, how they would interact with other vehicles around them, and how they would actually manage to also interact with infrastructure. So how they would accommodate merging activities, stopping at traffic signals, and changing lanes, and so on. Okay, so as I mentioned before, there were a number of cities who also are involved in the CoExist project, and these cities are spread throughout Europe, and those cities actually look at a different aspect of the modeling tool that we're developing. So here we have a certain number of cities that look at the microscopic aspect, so the individual characteristics of how vehicles drive, and then we also have some cities that look at the macro perspective, so looking a little bit more about how the behavior of the vehicles can affect the wider traffic flow at a more macroscopic level as well. So if we look at a few of the individual characteristics of each of those cities which are part of the project. First of all, we'll run through Helmond. Now, Helmond is the location of one of the project partners that's called TUS, and in Helmond is actually the test track for autonomous vehicles. So this is where we used the facility to test how the autonomous vehicles drive on the road network. And so this allowed us to look at different penetration rates, but also some of those infrastructure aspects. So looking at how vehicles interact at urban traffic junctions, things like vehicle to infrastructure communication, vehicle to vehicle communication, and also interactions within mixed traffic. So that existence of human controlled and autonomous vehicles on public roads, so that we can record that. And the information that we got from that was fed back into our simulation model as well. On to the next city, we have Gothenburg, and Gothenburg actually took a combined approach of both a microscopic and macroscopic allocation. And interestingly enough, there was also here looking at some of the shared space aspects, so how the coexistence of autonomous vehicles and human-controlled vehicles could actually influence modes of transport in perhaps some less formal infrastructure environments where we have perhaps plazas and piazzas in the middle of town where we see slow-moving vehicles, slow-moving pods through certain areas of the city interacting with cyclists and pedestrians and so on. And also then in Gothenburg looking at some of the longer-term construction as well. So whether or not the infrastructure that exists is resilient enough to accommodate a mixed fleet. So maybe in a horizon year of 2030, will having autonomous vehicles have enough capacity in the road network? Will the arrangement of some of that road network need to be changed in order to actually accommodate the vehicles and the level of penetration rates from autonomous vehicles that we would experience as well? Okay, well, on to Milton Keynes, and Milton Keynes really looking at quite a specific example and a micro example as well of how to operate the pick-up and drop-off activities. So vehicles pulling up outside buildings, passengers getting out of those vehicles, and then those vehicles driving themselves to a parking lot or a parking garage, parking the vehicles there, and then coming back to greet the passenger once they've finished their activity as well, and the types of technology that needs to be included in order to accommodate that. There's also an aspect of urban logistics as well, and this is looking at the use of small kind of delivery pods to make last mile delivery and collection as well. Okay, and the final location is Stuttgart in Germany, and this was focused very much on the macroscopic aspect. So this is looking at the capacity of the network with mixed fleets, also the designation of roads and routes to certain types of vehicles. So whether or not there's a segregation of autonomous vehicle only lanes or autonomous vehicle only roads within a city, and how that would actually affect other traffic flow, and how we might also look to influence some routing and journey movements that people make depending on the type of vehicle that they're using. So whether it's a human controlled vehicle or a autonomous vehicle as well. Also, ride-sharing systems are considered as part of the Stuttgart study. So this is where we look at car sharing, public ride sharing, how perhaps these types of modes can be used to support mass transit. So again, kind of first and last mile trips, which would support higher capacity public transport services as well, which really feeds into those kind of multimodal trips. So the fact that people may well leave their home, they take a shared bike to a station, then take a public transport train or bus service, and then when they reach close to their destination, they again take another micro-mobility mode in order to get to their final destination. So maybe an e-scooter and so on as well. Okay, so that was a quick overview of how the different study locations would actually operate and use the functionality that we were developing as part of this study. And now I just wanted to quickly run through some of those core tasks that really PTV were heavily involved in as part of the project. So we have the ability and the role that we are to make AV-ready traffic modeling tools. And this really is where we take our existing simulation tools and we extend those simulation tools in order to accommodate automated characteristics within that. So we have our microscopic transport models, we extended those to facilitate different types of automated vehicles. And from that, we looked at aspects such as safety, aspects such as traffic efficiency, and then clearly the demand or the space or the capacity of the road network, which then could be given as a guidance for hybrid infrastructure. So say, for example, here we can see an intersection where we have an on-ramp and an off-ramp, which creates a weaving section in between those two off and on ramps, and actually identifying how this infrastructure would need to operate in the future if we were to have a mixed penetration of traffic. So maybe if we had 10% autonomous vehicles in this infrastructure, would we see a difference in capacity compared to now? If we had 20%, 30%, and so on, would we see a bigger difference? And providing that guide and some information about how the infrastructure would accommodate those new types of technologies, those new types of vehicles as well. Okay, so now a little bit of the actual test bed itself. So here you can see some images of the public test track and also some photos of the vehicles that were operating along there, along with all of the kind of technical aspects that were included in those vehicles. So we recreated a real-time connection between the autonomous vehicle control logics as well as our tool, our microscopic modeling tools. So we have a live kind of digital twin of this area, which is running in simulation and uses the same AV control logic that is being used in the vehicles that are actually driving along that public road as well. So we can test further scenarios, perhaps add some extreme behaviors to how those vehicles are driving and test those out in simulation before we actually operate the vehicles on the public road itself. As part of that process, we looked at developing a set of model-based default parameters for AVs, as well as passenger cars and light vehicles as well. And that would allow us to provide functionality in the software where road authorities, but also traffic engineers, consultants around the world could take these default behaviors and integrate them into their own projects. So perhaps where you have ideas and challenges within road networks across the world about how autonomous vehicles could interact with infrastructure, what the impacts could be on capacity, on queuing, on delay, and all of these kind of aspects, being able to have that embedded in the software and accessible to all as well. So we ran the vehicles on this public test track and we extracted results from them. The vehicles were tested with a number of sensors, LiDAR, radar sensors on them. We also had GPS tracking so that we could take the trajectory of these vehicles, so how they were driving, also the speed, the acceleration, deceleration, and so on and so on. Okay, so from this data, we looked at taking our test track data and then improving some of our interfaces that we have within our software. So having some additional APIs that allow us to operate AV control algorithms within that test bed. So where we use simulation to create a digital twin of a test track and then testing specific AV control algorithms. So that's looking for use cases that focus around automotive manufacturers, OEMs, and researchers. And then, as I mentioned before, the internal approach where we have an improvement to our AV behavior, where we're providing a default autonomous vehicle driving behavior within the software, which can help transportation engineers, planners, traffic engineers, and so on, to start to test some of these scenarios, to reduce some of those assumptions that we need to make and look actually at how we need to perhaps amend the design of our intersections in order to accommodate varying penetration rates of vehicles. Perhaps we need to add some flexibility into our design in order to ensure that the junctions still operate as we would like them to in a transition period between human-controlled vehicles and automated vehicles as well. And we took those results from the micro perspective, so looking at those trajectories, looking at how vehicles follow each other, how they close up gaps, how they accelerate away, the delay that causes, and then applied that to macro functionality, where we actually looked at developing volume delay functions that can be applied in macro models and larger scale models, which can start to be used to consider capacity at a macro scale. So as I mentioned in that Stuttgart study, if we apply autonomous vehicles at a 10% penetration rate across a city, what can we see as an impact on capacity? Do we see an increase in delay and vehicles starting to reroute to other routes? If we do designate certain routes to just be for autonomous vehicles, how does that affect the wider choices of others as well? Okay, now I showed you before the public test track, and you could see how that test track was along a certain corridor from the facility of TAS into the city, and that that test track included a number of intersections within it. It also had some merging sections and other infrastructure which autonomous vehicles are going to need to negotiate and to deal with when they're implemented on public roads. And as part of that, we also had a number of scenarios about how the vehicles themselves operated. So we would change the following order of the vehicles. So sometimes we would have the autonomous vehicles following a human-controlled vehicle so that we could see how it would react in this way. We would have an autonomous vehicle following a connected autonomous vehicle, so that the following vehicle wouldn't be able to communicate with the vehicle in front of it, but the vehicle in front was connected, perhaps to infrastructure, to other aspects. And we run a number of scenarios along our public test track where we were altering the order of these vehicles, altering the configuration as well, in order to give us a robust set of data and a robust vehicle trajectory that we could then actually start to influence and to build our autonomous vehicle logic in the software from itself as well. And we also looked at some of those predefined time gaps as well. So this is looking at how we could vary the following distance between each of those vehicles, the time that vehicles would react on others, and so on and so on. Okay, so now I'm going to run through some of that trajectory data, some of the outcomes that we actually took when we recorded these vehicles on the public test track, and how we've then taken that data and integrated it into PTV Vissim, which is available for our users now. So first of all, looking at some of that test track data outputs, we could see where we really were very interested in the difference between some of the following behavior of vehicles as they were traveling. So looking at things, variation between the non-connected and connected scenario and how those vehicles react. Now, if we look at the chart on the right-hand side, what we can see here is that as vehicles increase in speed, and they are not connected. So in the scenario which is demonstrated with the black line through the vehicle graphic, we can see that when vehicles are traveling up to speeds of 120 kilometers an hour, the distance between the vehicles is between 35 to 40 meters when those vehicles are not connected. And we can also, if we look at the data velocity, we can also see that there is oscillation between how those vehicles are accelerating in order to close that gap up to the vehicle in front of them, or let that gap grow as well, because these vehicles are not connected, so they are reacting upon the action of another vehicle. They're not communicating as to what that action would be. So there's a lag in that decision, and therefore perhaps an increase in velocity in order to take into account that. Now, if we look at the same diagram in the bottom of that chart, where the arrow is showing the graphic of the connected vehicle, you can see that the trajectory is a lot tighter, so it's a lot closer together. So in this trajectory, we can see that at speeds of 120 kilometers an hour, the vehicles are following each other at a distance of 15 meters. So a lot closer together than they are when they're not connected. And also, if we look at the velocity, this is also a lot smaller as well. So there's very little difference as the vehicles are pulling away. They're communicating, which means that they're pulling away together at the same time. And we don't see large gaps opening, which then need to be closed up as well. So you can see the difference between standstill distance, which is around 5 meters, up to following distance at 120 kilometers an hour of 15 meters, really showing that there isn't a lot of variation as the vehicles travel faster. So this was part of the trajectory data that we took from the simulation, from the public test track. And if we then looked at how that would compare to some of our default driving behaviors that we have in Vissim. So for those of you that are familiar with the software, you know that Vissim utilizes something called the Wiedemann car following behavior. And the Wiedemann car following behavior is a psychophysical model which looks to replicate the human nature of people driving. So if we look at the chart at the top of the screen, you can see that when we were running our scenarios of our autonomous vehicle, there was a very linear relationship between the speed that the vehicle was traveling at and the distance to the vehicle in front of it. So as the speed increases, so does the distance, the gap between the two following vehicles. Now, if we compared that to our default behaviors in Vissim, we can see that there's a lot of oscillation. So the lines look quite messy. There is a general trend where there is also that relationship between as speed increases, so does distance. But you can see by the circular nature of some of those lines that there's oscillation. Now, this wasn't really a surprise to us because, as I mentioned, Wiedemann is a psychophysical model. So it looks to replicate the way that we drive. And often human drivers will find it difficult to follow a vehicle in front of them with an exact distance. So sometimes we'll follow that vehicle and maybe we'll lose concentration and we'll close that gap up. Then we'll feel a little uncomfortable because we're too close to the vehicle in front. So we'll slow down a bit to let that gap open up again. And that's how we actually implement the following behavior in Vissim as it stands. And that's what the chart at the below on the slide actually shows, is that oscillation between speeding up and slowing down and the impact that that actually has on the distance to the vehicle in front. But clearly, from the data that we collected on the public test track, this was something that we needed to overcome because we needed to actually calibrate to that data, that trajectory information that we had collected in order to make our driving behaviors in Vissim more replicate the use of autonomous and connected autonomous vehicles as well. So as you can see, we then looked at adding automated vehicle behavior parameters. So we actually expanded on some of those Wiedemann parameters to remove some of that oscillation and allow us to have a much more linear relationship between distance and speed. And here the colors are not representing the colors in the previous chart. The colors here are representing the different driving states that our simulated vehicles have. But this was where we actually went through that calibration process, that verifying the trajectory data that we'd collected on site for our autonomous vehicles and influencing and changing parameters within our default driving behaviors of the software to make sure that we could replicate the same types of behavior as well. So now what I will do is actually run through some of those changes that we've made to the software in order to incorporate this type of behavior. So first of all, here's a video of actually Vissim running. So this is where we have our simulated vehicles, and within the list of our driving behaviors, we can see down here that we've added different driving behaviors that have an AV name, so representing that autonomous vehicle. So these are all available as defaults to all users of the software. Now, if we look at the actual simulation model, we can see in the top link or the top road that we have our urban motorized behavior. So this is just our default driving behavior. Now, the next line down is where we've created our AV cautious behavior. So here we have vehicles that are driving very safely. They leave quite large gaps to vehicles in front of them, and that's because they have something which is called a brick wall stop distance, which is always maintained. Now, what this means is that if the vehicle in front of the following vehicle were to turn into a brick wall, the following vehicle would still be able to stop before it actually hit the vehicle in front. So replicating that kind of quite cautious behavior. Now, the next following behavior that we have, indicated by the blue simulated vehicles, is our normal behavior. So this is where we look to replicate an existing average driver whilst whilst using autonomous logic. So this is replicating the ability of sensors to kind of measure the distance and the speed of other vehicles and react on that as well. And you can kind of see by the blue dots here, the blue vehicles moving, and looking actually at the counters on the right-hand side of the screen, that the capacity is slightly increased against what we would class as default human drivers, but not necessarily that significantly. So the following distance there is quite similar to what we would see in our default urban behavior as well. And then onto our kind of most extreme or aggressive autonomous vehicle driving behavior. And this is really where we consider that vehicles are all-knowing. So they're quite aggressive. They know whether a vehicle in front of them will brake. They'll know whether a vehicle that's on a side road would pull out in front of them. They have that connected functionality that allows them to follow other vehicles in front with a small distance, because they will be aware of the vehicle's intentions before that vehicle actually executes a maneuver as well. Okay, and again, for those of you who are users of our software, you can see within the list at the bottom, we have made the parameters that we've changed publicly available. So you can understand the scale of the changes from defaults that actually affect this type of behavior. So understanding if you change a value by a certain percentage, what that could actually look like within your simulation model as well. And as I said, all of these behaviors and following distances and those parameters that you see at the bottom are as a result of calibrating those vehicle trajectories from the actual test track as well. Okay, the other thing that we needed to influence, because as I mentioned, we ran scenarios where we were altering the control of vehicles from being connected to just being automated, meant that we actually needed to also influence the software where it needed to recognize the type of vehicle that it was following and then adjust its behavior based on that. So here we can actually see that playing out in a simulation where we have autonomous vehicles and we have connected autonomous vehicles. And as you can see, we have the autonomous vehicles are following the connected autonomous vehicles with quite a small gap, whereas the connected autonomous vehicles are leaving a bigger gap when they are following autonomous vehicles as well. So it's actually being able to influence and vary the following behavior depending on the type of vehicle that is leading or the type of vehicle that's in front. So that is where particularly interesting for things like platooning, where perhaps we would have large kind of freight vehicles, heavy goods vehicles, and so on, and actually being able to influence the behavior of following vehicles, where you could perhaps potentially have mixed platoons of vehicles also operating on interstates and expressways and so on. Okay, so now a little bit of information for how or what those parameters actually mean within the software and those that we've changed as well. So the first one, as I mentioned, is that we have added a parameter that is called in-force absolute braking distance. And this is where the following distance of the vehicle is defined by the braking distance and the standstill distance. So ensuring that if a vehicle were to stop abruptly, the vehicle that is following would also stop before it came into contact with that forward vehicle as well. So this is now an option that is available as driving behavior, a checkbox that can be implemented, and the impact will be that it will have a safe application within the software. So you will see that capacity, for instance, would drop because the vehicles are following each other with a larger distance than perhaps we would expect before, and that's to replicate perhaps in that transition between human controlled and automated vehicles, the safe aspect as well. We then have varied the number of interaction objects that the simulation can see. So previously, the way that Vissim dealt with upcoming objects were that we could define the interaction objects, and that would cover both infrastructure as well as vehicles. So for instance, as you can see in the diagram, if that value were to be set to 4, it would just accommodate the 4 objects that are in front of the vehicle. So it could be 2 vehicles, then a signal, and then a vehicle in front. Instead of a signal, it could be a speed limit change, and so on, just different aspects of the actual infrastructure. So the addition that we've made is being able to specify between objects and vehicles. So now we don't have to have a matching value for both, but we could actually have number of interaction objects and number of vehicles separately as well. So the idea there really is that perhaps we could have an automated vehicle which can see a signal head because it has vehicle to infrastructure communication enabled, but it maybe could only see 1 or potentially 2 vehicles in front of it because the sensors couldn't see through the leading vehicle. So for instance, here we may well have a mixed fleet where we have human vehicles and other automated vehicles. It could be that our connected autonomous vehicle is following another connected autonomous vehicle, but then there's a human controlled vehicle that is in between them and the traffic signal. So therefore it can't communicate with all of the vehicles in front of the signal, and therefore needs to maybe leave a bigger gap, and so on as well. Okay, you saw in the simulation how we can also vary that headway or the following distance depending on the class of the leading vehicle. So this could be that variation between autonomous vehicles and connected autonomous vehicles following human-controlled vehicles, allowing them perhaps to leave a bigger gap because human drivers are a little less predictable. Also, autonomous vehicles perhaps following larger vehicles. So, as I mentioned before, large freight vehicles, delivery trucks, and so on. So being able to apply those different behaviors to different aspects and different vehicle types as the simulation is running as well. Okay, another key aspect is taking away some of that randomness that we saw. So when we looked at those Wiedemann parameters and the Wiedemann oscillation of following which exists within Vissim, you could see that when we needed to replicate the autonomous vehicle, we needed to take away some of that randomness. So we can also remove some stochastics from our simulation. So this is an element of randomness that reflects our human behavior as well. And that means that certain distributions can actually be removed. So again, assuming that vehicles, when they are automated, they would travel at a specified speed because much like cruise control in modern vehicles, you can travel at a steady speed rather than a human driving, perhaps always having to maintain their foot on the accelerator pedal and perhaps applying a bit of pressure, then easing off. That actually gives a distribution of speed, whereas automated vehicles and new kind of other advanced driving assistance provides the ability for vehicles to travel at a constant speed. So being able to actually influence some of those stochastics has also been built into the simulation as well. We also then have increased acceleration, and this is particularly interesting when we look at some of that trajectory data as well. Looking at when we have vehicles pulling away from a traffic signal, for instance, if vehicles are automated but not connected, again, a vehicle will pull away and then the vehicle behind will have to react on it and then accelerate. And maybe it accelerates at a faster rate in order to close that gap up again. Likewise, when vehicles are connected, they need to pull away together to maintain a consistent headway. And when that happens, we also need to facilitate increased acceleration as well, so that we can actually have those two vehicles following each other at a constant distance. Okay, And another feature that was added was that we can actually set the occupancy of vehicles to 0 as well. So for those people that need to run simulations where perhaps the number of passengers are important, so looking at how services might operate in a city, picking up and dropping off. Currently in PTV Vissim, we would always require an occupancy of 1 because there would be a person driving that vehicle. But in the functionality that's been added, occupancy can actually be set to 0 to replicate that automation as well. Okay, so just to summarize really the next steps that are involved in CoExist and also what we've been doing with the software as well. So the next steps for CoExist are that the 4 partner cities are now taking the functionality developed in the software and applying it to their own infrastructure. So going through that process of testing their existing road infrastructure within their cities, looking at different levels of automation, looking at different penetration rates, consumer acceptance of those technologies, and identifying whether or not their infrastructure, their traffic signals, their on-ramps, their merge areas, and so on, can actually accommodate the new behaviors that we've seen as part of our real-world autonomous vehicle testing as well. And undertaking that assessment and looking at whether they need to make changes to their infrastructure as well. And here at PTV Group, we are also extending our automated vehicle technology. So we've also looking at developing platooning, so how we can more effectively platoon vehicles within the software, again, having that as a default functionality where people can simulate quite easily the impact of platoons, varying the size that those platoons are, varying the type of leaders, the speed that those platoons actually have as well. So as I mentioned, and just to wrap up really, these functions are now available in the software. So for those of you who do studies, who look at capacity assessments, who perhaps do simulation models of interstates, perhaps testing design years that extend to 2030 and so on for cost benefit analysis and so on, you now have the functionality where we can actually add automated vehicles into those simulation models to give you some idea of whether that infrastructure can accommodate these new types of technology as well. Okay, so thank you very much for listening to the webinar that we've given today. I've been watching Jochen as the webinar's been proceeding, and he's been typing answers to questions. So we will review those and also discuss some more with you as well. Just so you know, the slides will be available following the presentation if you contact info.us@PTV Group as well.
I see a question about if the recording of the webinar will be available. Yes, we will send a link out to all the attendees, and then probably a general link as well, and post it on the PTV America LinkedIn page.
Okay, so just to answer some of the questions that have come in, Jochen's been typing, but I think some of them perhaps would be interesting for all attendees. So one question has asked about different weather conditions and whether we looked at how the vehicles would react, perhaps in fog, in snow, and so on. The tests were done in kind of normal weather conditions, so there weren't any extreme aspects to it. The vehicles weren't also necessarily capable of dealing with those with those weather elements as well. However, those are types of things that can be replicated in a simulation. So looking at the actual output of those vehicles, looking at the control, if we understand the control logic of that vehicle, how that vehicle would interact in that environment, it's something that could be used in that kind of virtual testbed environment as well. Another question relates to lane change. Within the public test track, we didn't actually take lane change trajectory data, so it was focused on following. However, I mentioned before how we were looking at platooning. We are considering the operation of lane change for autonomous vehicles as part of platooning, because clearly vehicles will need to change lanes in order to form a platoon as well. So that is something that is being considered there.
Okay, Alistair, thank you very much. I think with that, we can probably conclude the public Q&A. We have a list of all your questions. We can respond to them individually. And if you have any additional questions, please feel free to reach out via info.us@ptvgroup.com is probably the easiest route, or to your PTV representative directly. We also have some additional sessions that are going to be coming up. The next one will be scheduled for April the 25th. We will be sending out a detailed agenda for that here in the next couple of days, so make sure to watch your email as well as the PTV America LinkedIn page for that. We will be launching a website specific to the series as well, so you'll be able to access the upcoming events as well as recordings of previous events directly. With that, I think we'll end the session. Alistair, Jochen, thank you very much, and thank you to everyone who attended.
Thanks very much, guys.